Okay, so today we are going to add something called wholes. So I'm going to walk through how to do a problem, then we will define it in our notes, and then we'll go through another problem if there's time. First of all, we're on number 7. This is in your notes packet. And so on number 7, we're going to go through the same steps that we just went through. Okay, so the first step, we would want to try to factor everything. So we would want to factor our numerator. Here we are. Okay, we want to factor our numerator, and we see 3x and 6 have a common factor of 3, so we factor that out, and we are left with x plus 2 in the numerator. Then the denominator. Remember, we want our two sets of parentheses to factor this. We've got x and x, and we're looking for two numbers that multiply to the 6 and that add to 5. So factors of 6 are 1 and 6, as well as 2 and 3, but the only pair, since this is a positive and this is a positive, that would add to a positive 5 would be 2 and 3. So it doesn't matter the order there. Okay. Now we are trying to find any zeros, also known as x-intercepts, poles, vertical asymptotes, and horizontal asymptotes. We will talk about the domain and sketch it as well. Okay, so as before, when we find zeros, earlier in our notes, on a couple pages ahead of this, we know that the zeros are found when we set the numerator equal to 0. Now this 3 does not have a variable with it. So since it does not have a variable with it, we do not need to set it equal to 0. It doesn't change. Okay, it's a constant 3. So I set x plus 2 equal to 0. Solve that by subtracting 2 from both sides to get x by itself. Sorry about this mark. And we get negative 2. So I know my function will cross the x-axis at negative 2. So if I label that right away, it's right there. Okay, then the next step that we've been doing is the vertical asymptote. Okay, and the vertical asymptote is when we set all the factors of the denominator equal to 0. So if I look back at the denominator, I could set the original equal to 0, or since I've already factored it, I can set the denominator equal to 0, or each factor. There we go, each factor. So x plus 2 equals 0, and x plus 3 equals 0. I'm going to put more space there. Okay, solve both of those and I get x equals negative 2 and I get x equals negative 3. I subtract 3 from both sides, subtract 2 from both sides. Okay. Here is the new problem. Hopefully you noticed that up when we factor the numerator and factor the denominator, from our practice of simplifying rational expressions, we had x plus 2 in the top, x plus 2 in the bottom. Now we can look at it there, but really your wholes are created when they are zeros of the numerator and of the denominator. So essentially when I set the numerator equal to 0 like we did here and set the denominator equal to 0, it's when that value shows up in both the zeros column and as a vertical asymptote. So if we go back to the zeros and the vertical asymptote, we see we have x equals negative 2 and x equals negative 2. So we are going to say, hey, these are contradicting statements. Okay? The zeros is saying, yes, my function is defined at that point. However, the vertical asymptote is saying, no, my function is undefined at that point. They contradict each other. So since they contradict each other, we have a whole. And it's just that we're going to draw a circle at x equals negative 2 on the graph. Okay? So we fill in here, our whole is at x equals negative 2. So a recap, if any x values are in both the zeros column and the vertical asymptote column, it is a whole. And we cross it out very lightly here out of the 0 column and the vertical asymptote column, saying we're not going to have it as a 0 or a vertical asymptote anymore. It's strictly just a hole. Okay? Then back to our horizontal asymptote. We look at the highest exponent in the numerator, and I see the highest exponent is a 1. Look at the denominator, highest exponent is that 2. So you're asking yourself, is the top exponent greater than, equal to, or less than the bottom exponent? So essentially you're comparing 1 to 2. And hopefully you can agree with me that the top is less than the bottom. Okay? Looking at our notes, our 3 cases, when the top numerator or top exponent, there we go, the numerator, is less than the bottom exponent, our horizontal asymptote is y equals 0. So drawing some of this in now. We don't have any zeros anymore, so I got rid of that. Okay. Vertical asymptotes, we got rid of x equals -2. It's undefined there, and we'll show that in a moment. But we have a vertical asymptote at -3. So I find -3, and I draw a vertical line or a dotted line in. Okay. Then at y equals 0, I have a horizontal asymptote. So y equals 0 is also where the x-axis is. So I draw that in. Okay. And then I take a look at the part of the graph that has the holes. Okay. And so here, I know I've got a hole at x equals -2. So I need to find the output when x equals -2. So to do so, you can either find that on Desmos, or you can do it algebraically. If you do it algebraically, then we would have to find the function without x plus 2. So if I were to cross or divide these out, I would be left with 3 over x plus 3. And if I put -2 into that function, okay, I would get 3 over -2 plus 3, which is the same as 3 over 1. So we have our hole at a value of -2 over 3. Now, like I said, we can find this using Desmos. You can estimate it, but big picture here, at this coordinate, -2 up 3, we will have a hole. Then again, you can either use a graphing calculator or Desmos to sketch your graph there. Okay. And from there, we'll draw on the other part, which on Desmos, we will see that it's looking like that. Okay. So we did the same steps, which we still need to do domain, but we did the same steps as we had been doing. We just added one extra step that dealt with holes. Now domain, as if you recall, will be all reals except when x equals whatever the vertical asymptotes are. Okay, whatever the vertical asymptotes are. Now, you have to use all vertical asymptotes. So this would be, and we look at the holes. So even if we crossed out the -2, it is still a hole. So it would be vertical asymptotes and this hole right here. So x cannot equal, or x is equal to -3 or -2. In our domain, we can't have those two values. Okay? So looking at our graph, I just want to draw your attention to something here. Okay, so I graphed our original function. You always, always, always put the original function into Desmos when you want to look at a graph or a graphing calculator. Okay, so just to see where we have an intersection with -2, 3, I want to show you what Desmos does. So here, I know that our hole is at x equals -2. So I put x equals -2, exactly what our hole is, into Desmos. And you can see that line. Now normally when I click on the line, do you see how it shows you where the line would cross the x-axis as well as where it crosses the other line? But there's no point here. And I can try to drag this, and it's never going to say -2, 3. It's going to dance around it, and over there for a second you can kind of see undefined right there. -2, undefined. That tells us there's a hole. Now just in comparison, I just want to compare it to a defined value of x. We know that -1 does have a value in this function. So if I put -1 into my function, replace x with -1, I will get an output. Okay, so if I show you that, do you see how this line, the orange one, x equals -1, where it intersects my function, the graph of my function, there's a point. Whereas x equals -2, where it's undefined, where we have our hole, it does not show that. Okay, there is no point there. Even if I click back on the line, it never appears, but on x equals -1, where it is defined, you do see that. Okay, so that's one way to tell that you have a hole. So if we go back to our notes here, I want to define, sorry, it's going a little slow. You go back to page 5. At the very bottom of your page, we didn't do the finding holes investigation, okay? But we skipped it this time. But we want to define holes. Holes are zeros of the, why won't it let me click? There we go. Of the numerator and the denominator. Okay, so holes are zeros of the numerator and denominator. So that means those values we found when we set the numerator equal to 0 and the denominator equal to 0, like this -2, it was a 0 of the numerator, 0 of the denominator. When they're in both categories, they become a hole. And again, I do not want us crossing these out to confuse that. That was just temporary visual. Okay. Hopefully that makes more sense. We'll do number 8 in another video here shortly.